So your test is in 1 week, a week from today. What are you going to see? I didn't put any multiple choice. You put your phone away, Alfie. It's not that important. Oh, I apologize. Wow, I'm just in kind of snag them form right now. I apologize. Uh, some of the questions you're going to see, I will lift right from this quiz. It says a circular loop of wire has a diameter. I won't try and trick you on the test. I saw the diameter of 0.1 meters. I said, you know what? That means R equals 0.05 meters. We use radii in our equations, not a diameter. And it wants the average induced EMF. This is a loop, so I'm going to use Faraday's law, which is negative n change in flux over change in time. What's n? It said a circular loop. So I made a little list. I said, hey, n is 1. And then Presley, I typically find the delta t. That's the next easiest one to find. Let me pause the video for a second while someone comes in. I got delta t next because that was kind of plug and chug. What I usually do is I tend to find the change in flux off in the margin. You can do this all in one step if you're feeling bold. I said, okay, the change in flux is going to be the final flux minus the initial flux. Oh, wait a minute. It's removed. Jazz and Deep, if it's removed from the magnetic field, what's the final flux exactly as a number? What's the final flux exactly as a number 0? So I said it's just going to be negative B times A, and it's going to be the initial system. I said, okay, the change in flux is going to be negative. B is 0.5. A, it's a circle, so it's going to be pi r squared, which is going to be pi times 0.05 squared. And I walked that over to here. I said, okay, now I'm good to go. The induced EMF is going to be negative. I'll write the 1 just to let you know I did count the number of loops. It said change in flux is going to be negative 0.5 times pi times 0.05 squared divided by 0.2. I'm doing some really quick math in my head. I don't think we're going to get a big voltage here. What's a negative times a negative? I skipped typing that then, and I skipped typing the 1. I said, okay, 0.5 times pi times 0.05, don't forget the squared, divided by 0.2. Did you get 0.0196? Yeah, not much. 0.0196 volts. If you got that right, I would give you 4 out of 4. Otherwise, I'd probably give you 1 mark if I saw that. I'd probably give you 1 mark if I saw that, 1 mark for the numbers, and 1 mark for the answer. Now, here we have a single wire. You can use Faraday's law for that. It's adaptable, but what I would recommend when it's a single wire with a length, I would use the induced EMF equals BLV. And this one was straight plug and chug. On your test, I would have no problem since this equation has 4 variables, giving you any 3, find the 4th. Here I'm actually asking you to find the induced EMF. I would have no problem giving you the EMF and then saying, okay, find the velocity. Okay, anyways, it's going to be 0.4 times 0.5 times 25. Is it 5 volts? Am I right? Did the math in my head. Yay. If you got that, 2 out of 2. Otherwise, I'd probably go 1 mark for recognizing that it's that, half mark for the numbers, and a half mark for the answer. Now they want me to find the current. Current is V over R, although I guess I could write it as induced EMF over R. It's going to be 5 divided by 6. I'm pretty sure 5 over 6, isn't that 0.8333333, is, I think. Or am I wrong? I think I'm right. Again, 1 mark, half mark, half mark. I like number 3. I like number 3. Number 3 is a nice question. The magnetic field is changing direction. I chose to let this be negative and this be positive. You could have done it the other way around, in which case, Tony, you'll get the same answer as me, but yours will be negative, and I give you full credit. In fact, if you look at the ultimate review, often you'll see the answer says plus or minus whatever the voltage is. I would take both. It wants the average induced EMF in a coil. Again, I'm going to use Faraday's law, which is change in flux over change in time. Again, I'm going to make a quick list. This time N was 750, and this time the change in time was 0.25. But now I'm going to have to do a little more work. The change in flux is going to be final minus initial. What's changing isn't the area. What's changing, though, is the magnetic field. So the final magnetic field is negative 0.45. And they gave me the area. I didn't need to go pi r squared. They gave me the area, which by a coincidence was also 0.45, minus the initial magnetic field was 0.75 times 0.45. I continued to find this here, and then I'll walk this number over. If you wanted to move that whole, wrong button. If you wanted to move that whole expression over, you could, but I went, let's go to my calculator. Negative 0.45 times 0.45 minus 0.75 times 0.45, 5. I got a change in flux of negative 0.54 Webers, and I walked that over to here. I said, okay, the induced EMF is going to be negative 750 times negative 0.54 divided by 0.25. Negative 750 times, answer button, divided by 0.25. And I got an induced voltage of 1620, much bigger, volts. This would be maybe a small generator putting out a pretty good voltage. If the coil has a resistance of 100 ohms, what's the average current? Okay. I equals the voltage divided by the resistance. It's going to be 1620 divided by 100. I can do that in my head. 16.2 amps. For part marks, 1 mark, half mark, half mark. The previous one worth of more marks, 5 marks. I would probably do something like this. I think I'd give you 1 mark for recognizing it was Lenz's law. I would probably give you 1 mark for the answer, 1 mark for that. I'd probably give you 1 mark if I saw that, and 1 mark if I saw the Webers somewhere. Or if I saw that expression, either or. Turn the page. Okay, now we're doing a loop of wire. Okay, this length is moving perpendicularly. They want a speed. You know what? I'm pretty sure I'm going to be using BLV. And I'm going to get the speed by itself, which is the voltage divided by the magnetic field times the length. The voltage is 0.75. The magnetic field is 0.25. And L was 0.42. 0.75 divided by bracket 0.25 times 0.42. I got 7.14 meters per second. One mark. Actually, I'd probably go like this. 1 mark if I saw that. 1 mark for the numbers, 1 mark for the answer. What else can I find? I can find the current through the resistor. V over R is going to be 0.75 divided by 0.75 divided by 0.5. Oh, I can do that in my head. Is it 1.5 amps? No, yes? Yep. Other questions I could ask, but I didn't, but I'll give you a hint because you might see this in the future. Now that you know the current, I could ask you to find the force on the wire, Bill. That would work. The force will be tugging it backwards against the direction that it wants to move. The final question, what direction does the current flow through the resistor, from A to B or from B to A? I can do this two ways. I can use Lenz's law. So Lenz's law says, what is the change in flux? It looks like we're exiting a field going into the page. It looks like we're reducing a field into the page. What would reduce a field into the page? A stronger field coming into the page. So I'll point my, oh, you know what? I think I did this. Hang on. Am I doing this right, Mr. Dueck? I did this wrong with my morning class. I'm going to have to go correct their quizzes. Boy, I do this right with you. So if we have a reducing magnetic field into the page, we want to increase the magnetic field into the page. If I point my thumb into the page, the current is going to go in that direction. That's what Lenz's law says. Okay, now the other way I could do it is with my right hand rule. There's my proton. I don't care about these two because they're parallel to the direction of motion. They're not going to induce much of a voltage. What direction is that proton traveling? To the right. Everybody point your right thumbs to the right. Magnetic field into the page. Which way will that proton feel a force? Up the page, and we'll get a current going, I think, from B to A. Is that correct? Oh, and as soon as that happens, not only now is there the proton moving sideways, it's moving up. If I point my thumb up the page, fingers into the page, there's now a force tugging against you. That's where Lenz's law is kicking in and saying you get nothing for free. Can you give yourself a nice clear score out of 21, please?